Hi, I'm Chris, and in this chemistry lesson we're taking a look at KSP. KSP is your solubility product constant, and it's going to work just the same as your equilibrium constant. So if you haven't yet seen equilibrium, or you don't know how to come up with the expression for your equilibrium constant from a chemical reaction, then you want to take a step back and go and make sure that you learn equilibrium constant K first. If you're comfortable with that, we're now going to take a look at your solubility product constant. And that's essentially going to be your equilibrium constant for the dissociation of a solid in solution. So here we're looking at AgCl, which is silver chloride, dissociating into Ag plus and Cl minus in a solution. Now, when coming up with your expression for KSP, just like with your equilibrium constant, you're going to look at the concentration of your products over your reactants. The only difference here is that your reactant is a solid, and as you may remember from equilibrium constant, we do not include pure solids in the expression. So it's just going to be the product of your concentration of your different products that you have. You're going to multiply those together. For this first example, we're using a situation where we have a coefficient of 1 for everything in the reaction. In our next couple of examples, we'll take a look at what happens when you have dissociation of something that in the balanced reaction has coefficients on the product side. That's going to change the way we do calculations a little bit. But for this calculation, what's also important to note is that here we're going to start with 0 for our initial concentration of each. And if you set these up with an ICE chart, which stands for initial, change, and equilibrium, that's going to be the easiest way to figure out what actually happens in your solution as something dissociates. So right now we're looking at a solution that has no silver ions and no chloride ions to begin with. And we're going to take a look at what happens as that silver chloride dissociates. So we put our silver chloride into our solution. Let's say it's a cup of water, and we put some AgCl in it. Some of the silver chloride is going to dissociate, and we don't know how much that is, which means these will be your variables. So here you will have plus X and plus X for the amount of silver ions and chloride ions that form in the solution with the dissociation of AgCl. So when you add up everything, that tells you where you are at equilibrium. So we get X for each of those. And for your KSP expression, like we mentioned, KSP is the product of the concentration values of each of your products in the reaction. So you're going to multiply those concentrations together. Ag plus times the concentration of Cl minus will give you your KSP expression. And here's where we plug in those values of X. And X, just so we know what it stands for, X stands for molar solubility, which basically is a way of saying, okay, how easy is it for this to break up in your solution? How likely is it that you end up with lots of these ions when something dissolves? So when we plug in X for Ag and when we plug in X for Cl, your KSP expression will look something like this, X times X. So your KSP will be equal to X squared. Now for the mathematical part of it, this is just the setup. But for the mathematical part, oftentimes when dealing with KSP, you're going to be given a KSP value and asked to find the molar solubility, which means you're given the KSP value and you're asked to solve for X. So here, for this particular substance, silver chloride, AgCl has a KSP of 1.8 times 10 to the negative 10. Now let's do a little math exercise on this. If we have to take the square root of a number in scientific notation, we're first going to start with this number out front, which we call the mantissa. And we're going to take the square root just of that value. So the square root of 1.8 comes out to be about 1.34. So when we square root both sides here, we get 1.34 times. Now here, 10 to the negative 10, when you take the square root, all you're going to do with this part of your scientific notation is you're going to divide the exponent by whatever root you're taking. The square root of something to the negative 10 will be to the negative 5. And I think that's 1.34 actually, if we look at that even a little bit more exactly. So then here, 1.34 times 10 to the negative 5 will be your value for X, or in other words, your value for your molar solubility of silver and of chloride when dissolving AgCl in a solution that has no common ion effect. There's no silver or chloride ions in the solution to begin with, and this is going to be the value for molar solubility. Now in our next example, you can click here and watch, but we are going to look at some more complex scenarios where we have coefficients to deal with and where we have common ion effect, where we're starting with an initial concentration of some of our ions to begin with. So stay tuned for that, and thanks for watching.